Time for 2D projectile motion part 2, where we solve some problems. Here are the problems we're going to be solving. I'm going to put them on the screen and then pause for a second so that you can pause the video and work them out before I work them out for you. So here they all are. Here's question 1 and 2. Here's question 3 and 4. Here's question 5. All right, let's get started. Here's our first problem. It's about two toy trucks that are being launched horizontally off a table. The table is the same height in both cases. And it says, in a clear, coherent argument, explain which toy truck will travel the farthest horizontal distance before landing on the ground. So here we go. First thing to realize is we have a horizontal launch. That's important. Number 1. Number 2 is to remember that the X and the Y motion are separate. They're independent of each other. Okay, so now that we know that, we can break this motion down into its X and Y components. So in the X direction, one of them is going faster. And remember that X equals Vx times t. It's constant velocity. In the Y direction, though, we have acceleration. So Y naught Y, Vy naught, Vy, A, and T. I'm going to call this 0 and down positive, okay, since everything's happening in the downward direction. And so they both start with 0 position and a 0 initial velocity. They're both going to land at a height of h. They're going to move downward h, positive. And they both have an acceleration of g, which is positive since down is positive. All right, I do not know what velocity they're going to land at, but I can write an equation for the time. So y equals y naught plus Vy naught t plus 1/2 at squared. Let's cross off the things that I know are 0. This is 0 and this is 0. So I'm left with h, how far it falls, equals 1/2 gt squared, or the time for it to hit the ground will be 2h over g square root. I want you to notice this is the same time for both. That's important. So that's our key thing number 3. Takes the same amount of time for them both to hit the ground. If they have the same time to hit the ground, then the one that goes the fastest will go the farthest because x is proportional to v. Since the time is the same, all that matters is how fast they're going. B is going faster. So this is number 4 important thing, and number 5 is our answer. B goes farther. Now we have to put this into a written argument. Now it's not that hard, so all you have to do is go through these steps. You have to say the x and y motion are independent. This is a horizontal launch. Therefore, the time it takes for them to hit the ground will be the same. Since the time is the same, and one of them is traveling faster at a constant velocity, then B will have to go farther. And there you go. That's how you string that argument together. Let's take a look at our next problem. In this one, in a classroom at time t equals 0, a sphere is thrown upward at a 45-degree angle to the horizontal. At a time t1, while the sphere is still rising, that's important, it bounces off the ceiling both elastically and with no friction. Okay, so elastically means that it's not going to lose any speed. It's going to keep its kinetic energy. And then no friction means that there is no force to slow it down. So let's take a look at what a ball would look like if we just threw it straight up or at an angle in the air. So it would look something like this. Here's the ball, it goes something like that. Now it's going to hit a ceiling while it's still going up. So here's the ceiling right here. So it's going to cut off this top part of the motion. So it's going to look, it's like this part gets moved over here. So we end up with a motion that looks like this. So there's a little bit of a notch right there, or a V shape, I should say, where it doesn't slow down at all. So its x direction motion is going to stay the same. its y motion is going to be on the way up, the same as on the way down. It's just that this top part gets chopped off. So its x motion will look like this. Here's Vx versus time. So its x velocity is just going to be constant the entire time. So there's our answer to part B. Here's what it looks like for part A of the question. And part C says, well, what does the vertical velocity of the ball look like? And here's Vy versus t. So the ball initially starts with a y velocity up, and it ends with a y velocity down, and these two should be the same. So there should be one here, and there should be one over here. And here is the time t1 where it hits. Okay, so it's slowing down on the way up, and then it hits the ceiling, and then it slows down or speeds up on the way down. So this slope should be negative g in both cases. All right, so that's what it should look like. So it's just got this little notch in it in the y direction. Here's our next one. So in this particular problem, we have a cannon that's firing all of these cannonballs. They have different masses, but we already know for projectile motion and kinematics that, that the mass doesn't matter, right? So that's irrelevant. We can cross that out right now. They're all launching at a 35-degree angle, so the angle is the same in each case. It says, first, rank the acceleration of the cannonball when they reach their maximum height. Well, okay, they're in projectile motion. They're at the top. The only force acting on them is gravity. Therefore, their acceleration down must be g. So they're all the same acceleration. Easy. Okay, now our next question says rank the horizontal distance the cannonball will travel. Now this is a little harder. So first thing we need to realize is that x equals vxt. The x motion is separate from the y motion. Okay, and in the y motion, it's a bit more complicated. This is constant velocity in the x direction. That's easy. In the y direction, let's make our table. Y naught y, Vy naught Vy, A, and T. So if we call where it begins right here, let me use a different color, right here, our height or y equals 0. Then, and assume it lands at the same height. So I like to say that little bit of height of the cannon doesn't really matter much, all right? So then this is going to start at 0 and going to land at 0, okay? I'm just going to say it's going to land at this same height. The initial y velocity, all right, this is an issue. It's being launched at a 35-degree angle. This is the velocity. So the x part is going to be v cosine of 35 degrees. And the y part is going to be Vy equals v sine of 35 degrees. Important, we have to separate them out because the x and y can't mix when we're separating them into x and y components. Y velocity to begin is v sine of 35 degrees, and it's going to land, since it's going to land at the same height, it's symmetrical. It's going to land at negative v sine of 35 degrees. Same velocity up and down. The acceleration is going to be negative g, so I have chosen up as positive because it starts up, then comes down, and the acceleration is down. I don't know the time, but I need this time to know how far it's going to go. So let's find that time. How about we use these and let's use v equals v naught plus at. So our landing velocity is negative v sine of 35 degrees. Our launch velocity is v sine of 35 degrees minus gt. I'm going to solve it for t. So I'm going to move this to this side. That'll double this negative. My negatives will cancel. So I end up with t equals 2v sine of 35 degrees over g. There's our time. I want you to notice that the time is proportional to the launch velocity. 35g and 2 are all the same for each one of these launches, right? They all have the same angle, and they all have the same gravity pulling them down. So that means that as the velocity goes up, the time goes up. That's important. So now if we pass that information over here, we get that x equals all of this time times the x velocity. But we know the x velocity is v cosine 35 degrees times this time. Now look, that means x is also proportional to the velocity and times the time. So as the velocity goes up, the time goes up, and as the velocity goes up, x goes up as well. So there's two reasons why the one that gets launched with the highest speed will go farthest. There's two reasons. Number one reason is that time in the air is longer as v increases. And then number two, x equals velocity times time. So the time is bigger, and now also the velocity is bigger. Bigger velocity equals more x. So I have two reasons. More time in the air, and I have a bigger velocity in the x, which gives us more x distance anyway. And there you go. So the ranking would be, let's see, the one with the highest velocity. So our ranking would be A goes the farthest, D goes next, and then B and C are the same. Time for our last problem. So we have two identical spheres that are released from a device at time equals 0. It drops sphere A straight down, and sphere B gets launched to the side. It lands a distance d away from where it started horizontally, and they both fall a distance h, and they both hit the ground at a time tf. All right, first question. The dots represent the spheres. Draw a free body diagram for each one. Okay, here's sphere A, here's sphere B. They're identical. So they have the same mass. If they have the same mass, then they've got the same gravitational force. And two things to always remember if you have to do this on the AP exam. Always draw these arrows distinctly to one of these dashed lines. That's what they're there for, so that the reader can understand how far you're drawing your arrow, and to figure out if the arrows are the same length. So you draw them to the same dashed line. Don't give them the opportunity to make a judgment about what you're thinking. Okay, draw it directly to that line, and always draw your arrows facing away from the point. There we go. And you can also mark them as the same just to make sure, so that there's no confusion. So that's the answer to part A. Part B, on the axis to the left, sketch and label the graph of the horizontal component of the velocity. Well, wait a minute. Look up here. A has no horizontal velocity at all, no x velocity. So its graph should look like this. It should be 0 down here. And I'm going to do this for emphasis. I'm going to make an ending spot, TF. Remember to label, oops, you can't see that. Remember to label the times. It gives you a time TF, mark the time TF, that's when it hits the ground, that's when it ends. And then our other sphere has a velocity to the right, but its velocity is constant. So it's going to go over here, and it will also end at this same vertical spot, TF. Now, label your drawing. Label it. If you do this, it's no points because you haven't labeled them. So this is A and this is B. They don't know if you don't label, so make sure you label them. Our last question is the same question, but it says, in a clear, coherent paragraph-length response, explain why the spheres reach the ground at the same time, even though they travel different distances. This one travels a much larger distance than this one does, so why does it hit the ground the same time? Okay, remember our A, B, C, D format. A is for answer the question. it says explain why the spheres reach the ground at the same time, even though they travel different distances. So you have to address both those issues. That's the question. B is, what is the basic physics involved? Well, first of all, our basic physics is that the x and y motion are independent. Okay? And the second thing is that the initial y velocity, y initial, equals 0. I should put a 0 down there. That means the time for them to fall will be 2h over g from our last problem, right? So that means they take the same time to hit the ground if they're at the same height. So that's part C. A, answer the question. B, give the basic physics. C, cite critical information from our problem. Our problem is that they have the same height. You see that if they have a different height, they don't hit the ground at the same time. So, and they both start with an initial velocity of 0. So you could put that here as well if you'd like. So our argument is made. So all we have to do now is D, draw our argument together. So my argument is that the x and y motion are independent. And since the ball is starting with a 0 velocity in the y direction, the time to fall will be the square root of 2h over g. And since they start at the same height, therefore they hit the ground at the same time, and it's independent of the x motion. And we're all happy because we got full credit. Great job, everybody.